Welcome to the Explainer. Today we're taking an incredible journey straight into the heart of renewable energy. Now we see solar panels everywhere, on rooftops, out in vast desert arrays, basically powering our everyday lives. But have you ever actually stopped to wonder what it takes to capture the sun's energy with such high efficiency? We're going to explore the astonishingly precise microscopic manufacturing of monocrystalline solar cells. It's a process where literally every single atom counts. And then we're stepping off the factory floor and out into the real world to prove exactly why all that painstaking, expensive precision is actually worth it.
Here is our roadmap for today. First, forging the silicon ingot. Second, slicing and texturing wafers. Third, printing and module assembly. Fourth, monocrystalline versus polycrystalline panels. And finally, tracking the sun. All right, let's just dive right into it. We're going to build a high-tech solar panel from scratch, and then take our finished product into the field to pit it against its cheaper rival. Section 1, forging the silicon ingot. We're starting at the very beginning here, because to really understand high-efficiency solar, you gotta realize that it all starts at the microscopic level. To create a top-tier monocrystalline solar cell, you need silicon purity levels that are basically off the charts. We're talking exceeding 99.999999%. In the industry, they call this 6 nines purity. Why so high? Well, at the atomic level, even the absolute tiniest impurity, like a stray oxygen or carbon atom, is going to disrupt the flow of electrons and physically drag down the efficiency of the final solar cell. We are trying to build a perfect crystal lattice here.
To achieve this absolute perfection, the industry relies heavily on what's called the Krzyzewski method. Picture this. A furnace heated up to 1500 degrees Celsius. That is literally hotter than flowing volcanic lava. A tiny seed crystal is dipped into this glowing, molten silicon, and then it's pulled upward at an agonizingly slow rate, about 1 millimeter per minute, while constantly rotating. This process takes 40 to 60 straight hours to carefully grow a massive, single, uniform crystal ingot that can weigh up to 450 kilograms. It's crazy. Go too fast and the crystal fractures. Go too slow and your costs just skyrocket.
Now, what's really fascinating when exploring these cost drivers is the sheer price of precision. Pulling these perfect crystals takes a massive amount of energy. Energy consumption alone makes up 30 to 40% of the cost of forging the ingot. Throw in the silicon feedstock itself, which is another 50 to 60%, and you can see it's an incredibly expensive, grueling process just to get our raw material ready to go.
Moving on to Section 2, slicing and texturing wafers. Once we have our massive, perfect silicon ingot, we have to transition to the cutting phase, where this giant crystal is sliced down into ultra-thin wafers. And this step reveals just how brutal that price of precision really is. To slice the silicon thin enough, around 180 to 200 microns, which is roughly the thickness of a human hair, factories use these incredibly fast-moving diamond-coated wires. But here's the catch. Because the wires themselves take up physical space, cutting the wafer literally destroys a massive chunk of the crystal. Up to 40% of that perfectly forged, super pure silicon is completely lost as sawdust, known in the industry as kerf. Imagine buying an insanely expensive cake and immediately tossing 40% of it in the trash just to slice it up. But the kerf isn't even the only problem. Think about it. You just took a diamond saw to a fragile crystal. The resulting raw sliced wafer is totally covered in microscopic cracks from the sawing process. And on top of that, it's incredibly smooth, which means it's highly reflective. If a solar panel acts like a mirror and bounces sunlight away, well, it can't generate power. So how do you fix a damaged, super reflective wafer? The answer is chemistry. They plunge these wafers into a hot alkaline bath of sodium or potassium hydroxide. This chemical texturing essentially eats away that damaged surface layer and, almost like magic, creates millions of microscopic pyramid structures all over the silicon. These tiny pyramids act like light traps. They bounce the incoming sunlight down into the cell instead of reflecting it away. It's a brilliant chemical bath that drops the wafer's reflectance to less than 10%, instantly winning back the efficiency that was lost to the saw. All right, Section 3, printing and module assembly. We are finally moving to the last stages of the factory process. We've got these perfect light-trapping wafers, but they're still just pieces of rock. They need to become functional, rugged panels that can actually transmit electricity. To get the electricity out of the silicon, we need conductive pathways. But every millimeter of the cell you cover with metal is a millimeter that isn't absorbing sunlight. So manufacturers use an ultra-precise screen printing process to squeeze incredibly expensive silver paste right onto the cell. They print these tiny finger lines that are just 25 to 35 microns wide. It's a massive balancing act, using premium silver to carry high electrical current while keeping the lines so impossibly thin that they don't block the sun from hitting the cell beneath them. Let's see how all these components build into a final product. First, the printed cells get strung together with copper ribbons and solder. Then, in a super fast automated process taking maybe 15 to 25 minutes, these really fragile cells are sandwiched between layers of protective glass and EVA plastic inside a vacuum laminator. Finally, pop on an aluminum frame and a junction box on the back, and you're good to go.
And the ultimate goal of all this meticulous, step-by-step assembly? Survival. A solar panel isn't some delicate lab instrument, right? It's designed to sit on a roof or out in a field, getting blasted by rain, wind, and baking heat. This tough lamination and framing process guarantees the panel is going to survive for over a quarter century outdoors, all while maintaining at least 80% of its original power output.
Section 4. Monocrystalline versus polycrystalline. We've seen the factory, now let's step out of that controlled manufacturing environment and into the real world for the ultimate face-off. We're going to test our highly engineered monocrystalline panel against a cheaper multi-crystal alternative known as polycrystalline. To see if all that manufacturing waste, high heat, and expensive silver printing actually mattered, researchers from IATIRA ran a rigorous 31-day field test in Indonesia. They put our monocrystalline panel right next to a polycrystalline panel on an automated dual-axis solar tracker equipped with real-time IoT monitoring. They ran this test continuously from 7 a.m. to 5 p.m. under the intensely hot, fluctuating tropical sun.
And wow, the crucial takeaway is massive. Over that 31-day period, the monocrystalline panel hit an average daily efficiency of 16.35%. The cheaper polycrystalline, just 7.11%. So yeah, that grueling, incredibly expensive factory process we just walked through, it absolutely pays off, with a huge, undeniable efficiency win in the real world.
The data perfectly illustrates how that efficiency translates into raw power. The monocrystalline panel's daily power curve peaks at almost 8 watts in this specific test setup, while the polycrystalline panel literally struggles to even hit half of that output. From sunup to sundown, the single crystal structure just captures and converts way more usable energy. And it's the exact same story when measuring the electrical current generated throughout the day. The monocrystalline panel, with its unbroken atomic structure and zero crystal boundaries to get in the way of the electrons, proves it is the clear winner. Those tiny silver-printed lines we talked about earlier are doing exactly what they're supposed to do, efficiently sweeping that current away for us to use. Section 5. Tracking the sun. Because believe it or not, the panel itself is really only half the equation when it comes to maximizing real-world energy capture. How you mount it changes everything. In this experiment, researchers didn't just bolt the panels down to a fixed rack. They utilized an automated dual-axis tracker system. It uses light sensors and servo motors to physically adjust both the side-to-side azimuth and the up and down elevation. By perfectly facing the sun at all times, the system completely avoids those huge drop-offs in power that happen when sunlight hits a fixed panel at a sharp angle. So to summarize the field test, tracking the sun actively boosts overall light capture and keeps power stable all day long. But here's the catch. Even with the best tracker and the purest silicon, physics is still physics. As the day heats up, panel temperatures spike. In the study, the mono panel reached over 44 degrees Celsius. This rising heat creates electrical resistance, which physically drags down the efficiency of both panels during the hottest part of the midday sun. Thankfully, integrating those IoT sensors means we can track all these precise temperature and power shifts in real time. Which brings us to the end of our journey today. We've seen the unbelievable atomic precision required to forge a silicon wafer, the chemical magic of texturing, and those vast real-world efficiency gains that just blow cheaper panels out of the water. But it leaves us with a really provocative thought. As our manufacturing pushes closer and closer to theoretical perfection, squeezing out every last drop of sunlight, is the true future of renewable energy going to be limited by the technology inside the panel? Or is it simply going to be limited by finding enough physical space under the sun to track and place them all? Definitely something to think about. Thanks for hanging out with me for this explainer, and keep learning.